Factoring can feel like a guessing game when you're asked to take an expression like this one and turn it back into its original two binomials. But it doesn't have to be all random guessing. I'm going to give you this simple checklist here, a repeatable playbook to follow in order that works every time so you can solve intentionally instead of guess. The first step in your checklist when you're trying to factor a polynomial is to always check for the greatest common factor. It's easy to miss, but that's where we have to start. So if we have a polynomial like this one, we're looking for the greatest number that goes into both of these terms, 6x squared and 9x. That number is 3, and we're looking for the largest variable, which is x. So we can factor out a 3x, and pulling that out of 6x squared leaves us with 2x. Pulling that out of 9x gives us 3. In other words, the factors of 6 are 1, 2, 3, and 6, and the factors of 9 are 1, 3, and 9. The largest common factor that they share is 3, and with an x squared and an x is the largest factor we can pull. So then, to determine what remains, we figure out what we have to multiply 3x by in order to get 6x squared. We have to multiply 3 by 2, and we have to multiply x by x. So what remains here is 2x. And then what do we have to multiply by 3x to get 9x? Well, just 3. That's how we pull out the greatest common factor. Once we've pulled out any common factor, then we want to look to see if what remains is a quadratic. And more specifically, we want to look to see if the second and third terms in the quadratic have the same sign, like they do here. We have a plus 7x and a plus 12x. Or if they have opposite signs, where one sign is addition and the other is subtraction. What we're looking for when we try to factor a quadratic are two factors that multiply to 12, whose product is 12, and whose sum is 7. The way to approach this is to start with the product question. So we look at the factors of 12. The only way to get two numbers that multiply to 12 are to multiply 1 by 12, 2 by 6, or 3 by 4. You always want to start at 1 and count up. So we started at 1, we got 1 and 12. Then we look at 2. Does 2 go into 12? Yes, it does. So 2 and 6 are a factor pair. We keep going until we cross over into the other direction and start getting duplicate factor pairs. For instance, if we kept going here and we looked at the next number, 4, we would say that 4 does go into 12 3 times, and we would get the factor pair 4 and 3. But that's the same as the factor pair 3 and 4, so we don't need to list it. There are only 3 unique pairs of factors that multiply to 12. So we start with that list. Then we look at the list and ask ourselves which factor pair has a sum of 7. And of course, 1 plus 12 isn't 7, 2 plus 6 isn't 7, but 3 plus 4 is 7. So that has to be our factor pair, which means this quadratic has to factor as x plus 3 times x plus 4. We just take those two values and we say x plus the first value and x plus the second value. It's important to note here that the order in which we list these factors doesn't matter. So if we took x plus 4 in the first binomial and x plus 3 in the second binomial, it doesn't matter because these two things are multiplied together. So think of it as saying 1 times 2. Of course, that's the same thing as 2 times 1. The order of multiplication doesn't matter. All we need to make sure we do is include x plus 3 and x plus 4 as the two binomials that multiply to this x squared plus 7x plus 12. This is the process we follow when the signs in our quadratic are the same. But when we have opposite signs, like we do here, we have a minus 8x and a plus 15, so we have opposite signs. Our process is a little different. We have to look at the sign on c, which is the constant term here at the end of the quadratic. When c is greater than 0, our factors are going to have the same signs as b, where b is the coefficient on this middle x term here. When c is less than 0, our factors are going to have opposite signs. So in this particular case, c is a positive 15, so c is greater than 0, which means our factors must have the same sign as negative 8. Negative 8, of course, is negative. That means our factors have to be negative values. So when we list the factors of 15, we only need to list negative factors. As always, we start at 1, and we can say that the factors of 15 are 1 and 15. Then we go to 2. 2 doesn't divide evenly into 15. Then we go to 3. 3 divides evenly into 15 5 times. So 3 and 5 are factors of 15. And then the next factor that divides evenly into 15 is 5, which is just going to give us a duplicate of the factors 3 and 5. So this is our full factor list. And of course, we make them all negative because they have to match the sign on this negative 8x. Now all we're looking at is the same question we looked at before with this same signs quadratic, which is which of these factor pairs sums to negative 8. And of course, that's -3 and -5, which when we add them together, give us -8. -3 and -5 also, of course, multiply to 15. So this has to be our factor pair, which means the quadratic factors as x minus 3 times x minus 5. To make sure we get this, let's look at the other scenario where c is less than 0. Here in x squared plus 2x minus 15, we have this -15, which means that value of c, -15, is less than 0. Therefore, our factors have to have opposite signs. One has to be positive, one has to be negative. So we list the factors of -15, and since we now have opposite signs, we have to include both sets, +1 and -15, and the opposite, -1 and +15. Also 3 and -5, and -3 and +5. Once we have these factor pairs, we're looking here for a factor pair that sums to +2, and the only one that does that is -3 +5, which means this quadratic has to factor as x minus 3 for the -3 times x plus 5 for the +5. Sometimes though, you're going to run into a quadratic that's going to give you a problem. We look at this one here and we see that c is +7. So we think, okay, that means the factors we use have to multiply to 7, sum to 5, and those factors have to have the same signs as b, which means the same signs as +5. They both have to be positive. So we list the factors of 7. 7's a prime number, so its only factors are 1 and 7. So we think, okay, we have to use this product pair, and they both have to be positive, so we have to use +1 and +7 to sum to 5. But it's impossible to use 1 and 7, both in their positive forms, to add to 5. The only thing they can possibly add to is +8, which doesn't seem to work. When that's the case, as long as you've been following this framework, you haven't missed anything or done anything wrong. We say that the polynomial is prime over the integers. This little z symbol stands for all integers. So if we're only going to use integers, we can't factor this quadratic, or we can't factor this polynomial. The only way we could factor it is by dipping into values that aren't integers or into the complex numbers, which we're not going to do here. So this polynomial is prime over the integers. Let's talk about the next step in our repeatable checklist, which is to look at coefficients. Let's assume here that we pulled out any greatest common factor, and we looked at these same sign and opposite sign methods for factoring the quadratic, and we still can't figure out how to factor it. That might be because we have a coefficient on our x squared term, some value that is not 1. When that's the case, we can use something called the AC method. And we previewed a little bit already that we refer to the coefficient on the x term as b and the constant term as c. Well, we refer to any coefficient on the x squared term as a. So you can always think about these coefficient values, or the constant here, as a, b, and c. The reason that we call this the AC method is because we're using these values here of a and c. And here's the method. We're looking for a factor pair that multiply to the product of a and c and sum to the value of b. So if we look at a and c, 2 and 6, their product is 12, which means we're looking for factors of 12, two values that multiply to 12. We know that they are 1 and 12, 2 and 6, and 3 and 4. Now we're looking for which pair here sums to the value of b, and of course that's going to be 1 and 12, which sum to 13. Now, this is all looking really similar. The difference here is that instead of going forward directly with factoring this quadratic, because of this coefficient in front of the x squared, what we're going to do is split the middle term of the quadratic, 13x, into two separate terms, each with a coefficient from our factor pair, 1 and 12. So 2x squared stays the same. Our 6, our constant, stays the same. But plus 13x, we're going to change into plus 1x plus 12x based on this factor pair that we identified. Then we're going to group the first two terms and the last two terms. We're going to think of them as two separate groups, and we're going to pull out the common factor from each group. So we're essentially going back to our greatest common factor step here. What's the greatest common factor of 2x squared and x? Well, it's just x, and what's left is 2x from the 2x squared term and just 1 from the plus 1x term. We'll do the same thing with the second group. The greatest common factor of 12x and 6 is 6, and what's left is 2x plus 1. When we use this method, these two binomials here are always going to match each other, which means that we have 2x plus 1 multiplied by x and also multiplied by 6. So we can pull that x and the 6 together into a binomial x plus 6, which is multiplied by 2x plus 1, and this is the factored form of the original quadratic. Notice here, I want to prove to you that the order of the plus 1x and the plus 12x doesn't matter. If we move the 12x to the first box and the 1x to the second box, and then we pull out greatest common factors again, we end up pulling out 2x from the first group and positive 1 from the second group, because 1 is the greatest common factor of 1x and 6. There's nothing else to pull out. That leaves us with the x plus 6 binomial from both boxes, and we end up again with the same factored form, quantity x plus 6 times quantity 2x plus 1. So the order of the 12x and the 1x, how we split up this middle term, doesn't matter. We're going to get to the same correct result either way. Now, if nothing in our checklist has worked so far, it might be because we're dealing with some other kind of pattern. What do we do when we have a polynomial like this one with only 2 terms? Well, this is what we call a difference of squares polynomial. And what we notice about this one is that it is literally the difference of squares. The first term is x, quantity squared, and the second term is 7 quantity squared, and we're taking their difference. When that's the case, our factoring follows a specific pattern, and the pattern is that we take this second value here, the 7, and we say x minus 7 and x plus 7 in our 2 binomial factors. The reason that this works is because when we multiply the binomials back out, we get x times x, or x squared. We get x times a positive 7, so plus 7x. We get negative 7 times x, which is minus 7x. And we get a negative 7 times a positive 7, or a minus 49. And you see that the plus 7x and the minus 7x in the middle cancel each other out, and we're left with just the x squared minus 49. That's why our difference of squares pattern will always work. We can also have the difference of cubes. Notice that in this polynomial, we have x quantity cubed and negative 2 quantity cubed, because 2 times 2 times 2 is 8, and we're taking their difference. And when we have the difference of cubes, we use this specific pattern here. We write this generic formula. In our case, a is equal to x and b is equal to 2. And that's going to factor as this right side polynomial here. One way to help remember this factoring is to think about the acronym SOAP, where we get the S, O, A, and P, because this first sign here is always going to be the same as the sign between a cubed and b cubed. This second sign is always going to be opposite. So if we have subtraction here, we have to have addition here. And this sign is always going to be positive regardless of what this sign is. So same, opposite, always positive, or SOAP will help you remember the signs on this right-hand side. In our case, like we said, x is a, b is 2, so x cubed minus 8, or x cubed minus 2 cubed, is going to factor as quantity x minus 2 times quantity x squared plus 2x plus 4. Now, one last thing we want to say about patterns before we move on to grouping. Sometimes we'll have a polynomial like this one, and we might think right away, we can't do anything to factor it because we have this higher degree exponent. We have x to the 4th, and we haven't seen anything other than x squared or x cubed. What do we do in a situation like this? We automatically can't use any of these techniques, right? Well, actually, this is something that can still be boiled down into the patterns we've looked at. Regardless of the fact that this is x to the 4th, we can see this as the difference of squares. This first term is still just x squared, quantity squared, and the second term is just 9 squared. So we still have the difference of squares even though we had a higher degree polynomial, which means we can factor it as the difference of squares, and we get x squared plus 9 times x squared minus 9. And this brings up another important point, which is that as you're working through this framework and this checklist, you always want to make sure that you're trying to factor the polynomial as completely as possible. And what we see here when we factor x to the 4th minus 81 is that this binomial that remains is x squared minus 9, and it itself is again a difference of squares, which means we can continue to factor it. This is the difference of x quantity squared and 3 quantity squared. So we can rewrite x squared minus 9 as x plus 3 times x minus 3. So always factor as completely as you can. And since we're talking about difference of squares and difference of cubes, let's just make the note that when we have the sum of squares, we think this is something that we can factor because we can easily factor difference of squares, when in fact, this is not factorable. This is prime over the integers. This is as far as this binomial can be factored. So if you see a sum of squares, easy to think that you can factor it further, but you actually can't. So definitely leave it alone. And then if you're interested in more about factoring higher degree polynomials, the rational root test is something we can use to try to identify factors when we're dealing with higher degree polynomials. We won't cover that in this video, but I wanted to mention it since we looked at something higher degree. So we looked at quadratics, specifically we looked at polynomials with 3 terms. And then when we looked at difference of squares and difference of cubes, we looked at polynomials with 2 terms. Now let's talk about polynomials with 4 terms. These can be great candidates for a method called grouping. We already saw a little bit what this looked like when we talked about coefficients and we looked at splitting that middle term, creating 2 separate groups. And this would also be a good candidate for the rational root test since we have this higher degree polynomial. But here we're going to look at this grouping method, which is exactly what it sounds like, where we group 2 terms in the polynomial together separately from 2 of the other terms. For instance, here we took the first 2 terms, x cubed minus 2x squared, and the second 2 terms, 3x minus 6, and we created 2 groups. All we're doing now is pulling out the greatest common factor from each group. When we do, we see that we're left with this common factor of x minus 2 in both groups. So we pull together their coefficients x squared and positive 3 to create this binomial x squared plus 3, and this is the factored form of this 4-term polynomial. The biggest question here is how do we know which terms to group together? Well, your key is going to be to look for 2 groups, making sure that both groups share a common factor. So when we group the terms this way, we could see that these first 2 terms shared a factor of x squared, and these second 2 terms shared a factor of 3. Because both groups shared a common factor, we knew that this was going to work out. We can also group together the x cubed and the 3x term because they share a common factor of x, and the negative 2x squared and negative 6 term because they share a common factor of negative 2. It doesn't matter what the common factor is, as long as both groups have a common factor. So here when we group the terms this way, we pull out the common factor from each group, and what we're left with is the opposite scenario. Both groups now share a binomial of x squared plus 3, so we pull those coefficients x and a minus 2 into their own binomial, and notice that these match, that they're equivalent. The binomials are just multiplied in the opposite order, which doesn't change the value of the factored form. What we can't do is group these together in such a way where one or both groups don't share a common factor. So when we take the x cubed term and group it with the minus 6 term, that leaves these 2 middle terms in a group like we've done here. The second group should be fine because we can pull out a common factor of x, but this first group here, x cubed and a minus 6, those 2 terms don't have a common factor. Their greatest common factor is 1. So we can't pull anything out there, and notice how the factoring doesn't work like it did with these first 2 groupings. Here, the binomial that remains in each group is x cubed minus 6 and a negative 2x plus 3. Those don't match, so we really run into a dead end. In other words, these first 2 methods work because both groups share a common factor. This last method does not because this first group here does not share a common factor other than 1. Just make sure that both groups share a common factor, and grouping should work to factor a polynomial with 4 terms. That's your go-to checklist, your foolproof step-by-step method for factoring polynomials. If you follow these steps in this order, you should be able to factor any polynomial you run into. The question though is, why does this matter? Why do we have to factor things at all? Well, I'll give you a couple of examples. The first is this zero theorem, which we usually learn about in Algebra 2. But when we have an equation like this one, x squared minus 1 equals 0, we factor this left-hand side because it's the difference of squares. So we know to factor it as quantity x plus 1 times quantity x minus 1. And then zero theorem tells us that when we have 2 things that are multiplied together and that product is equal to 0, at least one or both of these things has to be equal to 0. In other words, if we have p multiplied by q, and that's equal to 0, it has to be the case that either p is equal to 0, q is equal to 0, or both of them are equal to 0. That's the only way to make the equation true, which means that we can say that x either has to be positive 1 or it has to be negative 1 in order to make this equation true, because negative 1 is the value that makes this first binomial 0, and positive 1 is the value that makes this second binomial 0. In other words, we use factoring to solve equations, to solve for the value of the variable, and therefore this is something we'll use all the time. Geometrically speaking, this is going to give us the x-intercepts of a parabola in the plane. We also use this in calculus to solve limits. Without really getting into the calculus of limits themselves, I can still show you that we oftentimes have a limit problem like this one. Notice that the numerator of this fraction can be factored. This is, again, the difference of squares, the same one. So we can factor it as x plus 1 times x minus 1. That allows us to cancel the factor of x minus 1 in the numerator with the factor of x minus 1 in the denominator, and this fraction simplifies to just x plus 1. When we're trying to find the limit as x approaches 1, which is what this notation means, we're looking for the value of this function at 1. So normally we would start by trying to plug in x equals 1, but notice when we do that with this original function, we end up with 1 minus 1, or 0, over 1 minus 1, or 0. We end up with 0 over 0, which is a big problem mathematically and doesn't really tell us anything. But when we factor the numerator and we simplify the function this way, all we're left with is x plus 1. Now, when we try to substitute x equals 1, what we get is 1 plus 1, or 2. And we can therefore say that the value of the limit as x gets close to 1 is equal to positive 2. And factoring is the only thing that allows us to solve that calculus problem. So factoring is a fundamental skill that we use throughout all of math. And if you want to learn a lot more about simple and advanced factoring, including testing yourself and get access to fillable worksheets and workbooks and lots of multiple choice questions, make sure to check out my algebra courses, which are linked below.